Okay, now it should be. Can you see the screen there?
Yeah.
And ask them if they hear us. Okay.
Okay. All right, so we can take this diagram and we can start playing around with this guy, the jet that's radiated off. And you can start adding other things there. And a simple thing you can do is replace this gluon with a vector boson. And you can have this decay to leptons or quarks. This is what we call, in the case of a Z boson, right, this is what we would call mono Z, right? It's a Z boson plus MEC. You can also, if this actually decays to quarks explicitly, this is actually just a monojet, because you can have a W boson decay to two quarks, and if this W boson has enough energy, it's just a single jet. You can also replace this gluon with a photon, and you can do the monophoton analysis. In fact, this was the first kind of dark matter analysis that was done. People always thought that jets were too complicated, and so they started with monophoton. But it turns out we'll see the sensitivity. And then you can also replace this with something even more complicated. You can imagine replacing this gluon with a top. But once you get to this point, you have to start playing with your model. Because in this instance, to get a top, well, at least the easiest way would be to take your quark and then have a flavor changing coupling here. So you have a quark, and then you have a top, and then you have the top goes into the final state. So this gets quickly complicated. And if you want to get even more complicated, oh, and just as a note, right, this is also a monojet. If your top decays to quarks, so the top can decay to two quarks and a B quark, right? So two quarks from the W and a B quark, so three quarks. And so that's again just a monojet analysis. And if you want to just get even more complicated, you can actually do a mono Higgs analysis. And now what we're doing is we're replacing this jet with a Higgs in the final state. But at this point, if you want to start studying this, you start having more complicated models. So in this case, you can have a spin one mediator, but you can also have it coupled to in this case, it's a pseudoscalar, the case to dark matter, like a 2 Higgs doublet model. So it quickly gets more complicated, but for all practical purposes, from the experimental perspective, you're just replacing your mono jet with your mono whatever. And this gives us what we call the mono X class of searches. I'm for sure missing other final states, but you can just imagine once you know the model, you can just keep tacking on final states. So how do you do these searches? Well, for the most part, it's basically the same. You take the same idea, right? You replace your jet with something else like a photon, and then you can go ahead and do the search. And in fact, like mono W to quarks, this is just a mono jet analysis, right? It's the same. And really what you learn from each of these, well, we'll see, the monojet is typically the most sensitive, but these various final states will turn on and off and have changes in their production cross sections. It's a question?
Yeah, thanks. Really basic question, but how are jets? How are jets defined? Do they have to have ports in them?
Yeah, so a jet is just there's many definitions. I think the way I would perceive it is a jet is just a cluster of energy in an event. And there are various clustering algorithms to cluster it. For all practical purposes, jets, typically we don't cluster leptons, so we kind of remove them or we separate them out. So you tend to call jets and leptons exclusive. However, there are things like soft leptons and leptons in jets, things that you can get from like B-quark decays. And those we still call jets. So I think kind of, or when I call say lepton, I usually assume it's isolated, which means that there's really not so much activity around it. And then when I say a jet, it's really just some cluster of energy, and it's usually dominated by like hadronic particles. So there's usually a lot of pions. And, there's usually a lot of particles in general.
Okay, so the photon example isn't a jet piece, it's just a single photon? Or
Yeah, so the photon is typically isolated,
Okay,
right?
got it.
So, yeah, so it won't have as much activity. So that's what we look for. Like there are plenty of photons in jets, but we just call them jets. Okay, so I wanted to do analysis. All right, so just to give you an idea, each of these tell you something about the coupling, right? You can change this coupling and enhance this guy, for example. And the nice thing about this is that these analyses are pretty similar. So a W decaying to quarks, right? When the W has enough momentum, it's just boosted, right? So it gives you a single jet. So this gives us the same monojet topology. And you can just take a cone of energy, and as long as your cone is sufficiently large enough, the decays of the W will be in there. To identify it, the way we typically identify things like a W decaying to quarks is, well, you have to now actually start trying to reconstruct the mass of this jet. And there's a lot of different ways to do this. Don't really have time to go into this, but suffice it to say this is a rich field. And we typically use these days this MSDs, which stands for soft drop mass, which is a groomed jet mass. And just to show you it works, right here is a top events. And here you have like a bump. Here's your black points of data. And that's a bump actually from a W jet. The other thing we do for these W jets is we want to isolate the likelihood that this has two prongs. And the way we do that these days is through rather complicated deep neural networks. So here's kind of the current standard one that we use in CMS. Yeah, that's all I'll say about it. But again, there's a lot of discussion these days about what's the right network and how do you preserve simulation disagreements and agreements in your network, et cetera, et cetera. If you want to take, the other thing you can do is you can do other monojet topologies. So you can imagine taking a top jet. Tops are heavier, so we typically just take a larger cone. And then if you have a larger cone, you can get a W decay to quarks, and then the additional B quark all in a single jet. And then you can do the same scheme of running some deep neural networks to identify it, or also taking the mass and looking for a top jet. But the important thing to think about is that these are all just monojet analyses, right? It's just a jet plus met. And in this case, all we're doing is we're taking a subset of our jets and we're classifying them by some final state that increases their sensitivity to dark matter, right? So you can imagine, say, taking a W selection, taking your monojet analysis, and then splitting it into categories and having a vector as a final state. But it's all just plus met. And what does this mean in terms of the analysis? Well, this whole scheme of complicated fits, right, that I showed you for monojet, where we have many different categories all fitting simultaneously. Well, now you can just take your subset and run the same scheme of complicated fits, right? And it works. And in fact, this is what we do. We just end up cloning the analysis, and we run this all as one big fit, right? So it's one simultaneous fit. So our 400 free parameters go to 800 free parameters, or maybe a little less because we can change the binning, right? And you just keep running the analysis. It gets more complicated. And we got very excited about, and actually this is, in CMS, this is our current monojet analysis. It actually has multiple categories where we classify the jets by the period.
Yeah, thanks. How does changing the binning reduce the number of free parameters?
Oh, so each parameter is a floating bin. And so, if you have a lot of bins, you just have more parameters, right?
So wouldn't decreasing the number of bins decrease your sensitivity in some way, or?
No.
Okay.
So the reason we bin basically based on the number of events. At some point you can in principle like go to the limit of infinite binning, right? Do an unbin fit. And there's a point at which binning fine enough and going to the unbin, the sensitivity is the same. And it's typically at the point where you're at the level of the detector resolution or the kind of physics resolution that you're looking for. Since we're looking for kind of broad deviations, right? The binning doesn't matter so much. the reason we choose these bindings is it's usually based on some optimization that we basically go to the infinite bin limit, and then we kind of make coarser and coarser bins. Or if you know your detector resolution, you're looking for something that's kind of localized, you can kind of jump to that binning right away.
Gotcha, thank you.
I mean, yeah, choice of binning is pretty much, it's kind of an art form. Question?
Yeah. Yeah, I'm just confused as to how it doesn't reduce the resolution, because if there's a particular bin with an event, then if you make the bin narrower, then the bin should stand out more. There should be less noise in that bin. So
That's right. But if you're looking for signal, it's like in every bin. So like
okay.
yeah, like a monojet signal will basically just change the slope of this guy, right? It's going to be in all the bins.
Oh, I see. Okay.
Yeah.
Okay. Well, it's really not localized to one energy. It's across
No,
all.
it's
Okay.
across them all.
Okay. Thanks.
Yeah. All right, so now I just kind of want to flash through many results and show you met plus X. And just to give you an idea, right, it's using the same after we kind of got this technology of doing, let's say, using Z bosons to constrain Z bosons, W bosons to constrain Z bosons, photons to constrain Z bosons. We basically cloned this strategy for every final state that we could. And so we would replace the monojet. Right. We would, take these final states and have them mimic the Z2 neutrinos. But then we just replace the jet with leptons, right? So you can imagine a Z boson going to leptons. And so now these are all different processes, right? You now have WZ production, Z production, and like in principle, you can even have photon Z production. You can have all of these constrained the Z2 neutrino background. And that's effectively what we do, right? You just take your new process and now you have a different production, but you can do the same scheme of simultaneous bits to constrain the Z2 neutrino background. And yeah, that's what we do. But as you change the final states, some of these backgrounds final states are more important and some are not. So for example, this gamma Z, it turns out that the WZ and the ZZ are sufficient to constrain this process. You don't actually need a photon Z to do it. So you end up with a simultaneous bit of just 4 categories. And that's what it looks like, right? So these are the 4 categories. And this is split by, you have 2 leptons in your signal region, and then you have 4 leptons, and 1 control region, 3 in the other, and so on. And just as a note, the other thing is, since these final states also change, people like to split them into different categories to enhance various sensitivities. This one they split into a 0 and 1 jet category. It gave like a 10% improvement in sensitivity for some noise. Okay, so now we can just go and show a lot of these, right? So this would be, imagine now the W decays to quarks. You can also do monophoton, right? This is the monophoton analysis, and here are your categories. They still haven't done the gamma final state, but it actually will improve the sensitivity. There's actually, I think this paper is a nice paper about how to do it. And you can also imagine doing replacing your jet with a Higgs boson jet. And so here's the Higgs boson jet. Here's all, again, the same categories, simultaneous bits. Yeah, you can look at these plots later, but suffice it to say that there's no excess, right? Data and predictions agree. And in fact, for mono Higgs, since they're more, when you do a Higgs jet selection, some of these backgrounds change the relative ratios. And so in fact, they added a top control region to control the T2 bar background of the signal. And you can imagine doing something else like a mono top jet, right? So this is again like mono jet, but now you apply top tagging on your jet, and you can use the same control regions. And in fact, this one, they not only add a top control region, they also keep the photon control region. And so you have 1, 2, 3, 4, 5, 6, 7 different categories trying to fit your mono jet. So they're all constraining the various backgrounds here in one big simultaneous bit. And then you can start to actually make sensitivity plots, right? And kind of the message from all of this is that, well, monojet is your most sensitive. And this is just because the strong coupling is large. And so your rate of monojet production is just larger than the other ISR final state. So the monophoton is typically the second most sensitive. And so that's this dash line here, blue dash line. I guess the solid line is just the observed result. The expected is the dash. So I always compare the expected. The mono Z here is the least sensitive. And you can see, right, as you go from Z to photon to jet, things get more sensitive. And you can also just look at the coupling, right? This is the mono Z is the weak coupling. Monophoton is just the electromagnetic coupling. And then monojet is the strong coupling. Yeah.
So it looks like the mono Z is not at all sensitive to the off-shell processes, and the other ones are a little bit. Why is that?
It's just a cross section, right? So it's the same model, but when the cross section gets small, so when you go off shell, the cross section is much smaller, and so you just need to be more sensitive, right? So the production cross section of monojet is like, I think, 100 times that of mono Z, and so you just have more events, and so you can go off shell.
Okay, that makes sense. Thanks.
I mean, in your last slides with the yeah, it's possible that if you see a lack of events in determined in from being, and this what is implied by the physics of the
So if you have a deficit in any of these, so let's say your signal, right? There's a deficit. So 99% of the time, this is because there's something wrong in your simulation. And you have to go and understand what's going on. Yeah, but there are cases where there are signals where you can have deficits, right? So, and it typically happens when you have like interference. So if you were to take, for example, if we take our scalar mediator model and goes to top quarks, right? And the gluon initial final state. This actually will mix, right? With so this will mix with normal TT bar approach. So this guy, and then you can have a. So these guys will mix, right? Same initial state, same final state. And what happens is you get a mass distribution that has deficits. So the mass will give you an interference pattern. So this will be, if you just look at the top mass. So it can actually give you a deficit. So there are signals that will give you deficits, but it really depends on the physics. Usually there's something like interesting going on, like mixing between signals and backgrounds. But 99% of the time, a deficit just means your simulations. It's something wrong.
Yes. Could you go to the exclusion plots? Yeah, so I'm used to looking at exclusion plots with the mass on the horizontal axis and cross section on the vertical axis. How
Yeah.
do you convert your limits on your mediator mass into cross section, or how do you convert this guy to the normal?
Yeah. So why don't I say I'm gonna spend some time on how we do the conversion to like direct detection and stuff later on. So maybe I'll just say you can wait like
Okay,
half
cool.
an hour. Yeah.
Yeah, thanks.
So I didn't quite get the point. So why we were looking now at those different processes, like that you showed maybe 3 or 4 slides before.
Yeah.
Like with the leptons, I mean, why didn't we just set the lepton multiplicity to 0, and then we would have less background to look at it, and I mean, you'll still find the signal, no?
Yeah. Well, you'll still get signal, but right. The point is we wanna search for dark matter in every final state we possibly can, right? So we know it's less sensitive, right? But you can also, I'm just showing you one interpretation, right? So this is with the spin 1 model, but it turns out that, like, for example, the mono Z becomes very sensitive if you go to different models, right? So I'll show you the spin 0 and actually the relative contribution of these channels will change, right? So like, for example, mono Higgs, right? Mono Higgs, the mono Z gets hugely enhanced because you have additional diagrams, right? So I mean, fine, in this kind of spin 1 model, you know, the kind of standard WIM, it's not so interesting, but like if you switch to something else, it becomes interesting. So we'll see it in like 5 minutes. All right, so yeah, so now we can start. So that's kind of the simplest model, but now we can start asking, what about more complicated models, right? And so mono Higgs I didn't even show because in fact for the spin 1 simplified model, there is no mono Higgs. But you can modify your Z prime, right, by having the mass mechanism come from the Higgs, and then you can suddenly get a mono Higgs final state, right? And you can get, you know, some sensitivity plot, and you can even go and put this plot on this previous guy, right? This goes out to like 1.8 TeV, and you know, you can see it's competitive with the mono jet final state. And then if you have this flavor changing neutral current, right? So your spin 1 mediator can change flavor change, and it has a flavor changing coupling. You can again then make another mass dark matter plot, and you can in principle overlap this with your results. And you can compare all of these, and they're all actually of similar sensitivity. This, of course, you would only see these final states, right, if your dark matter had some modified coupling. So we search for everything all at the same time because we have the data. But if we were to make a discovery and we saw it, let's say, just in mono top and not in mono Higgs and not in mono jet, we would know immediately what the couplings are, right? So you can determine what's going on with the dark matter mediator immediately from the final states. So now I can do the same exercise with spin 0, right? So spin 0 particle has Yukawa couplings. So for kind of the standard production, we produce it through a top loop. And again, you can make it a pseudoscalar, right? A lot of people like to call these ALPS, right? Axion-like particles, so pure CPI scalar. And again, you can start playing games with the final states, and they're going to be different. So here's the monojet final state. So we have a jet, we have our mediator. But then we can, now we have a different final state. Because of the Yukawa couplings, you can now have TET bar as well as DB bar, right? So you can, these productions will be enhanced because of the Yukawa coupling here. You can also have a single B or single top production, right, with your mediator decaying invisibly. And then of course you can do mono Z, right? So you can replace this loop with the Z. And actually the clever theorists will complain and say, well, you can't do that in the case of a scalar on the right. So you need you actually need oh no, sorry, you can do this with a scale. You can do mono Z, but you can't do mono photon, right? Because that would break Furry's theorem, right? Mono photon doesn't exist in this final state. And then if you have electroweak symmetry breaking in your mediator, and so it actually couples to vector bosons, right? Then you can have this mediator being produced by vector boson fusion. So you can imagine this be your X. It turns out that if you have electroweak symmetry breaking, and I'll talk about this in a sec, this guy is going to mix with the Higgs. And so you typically are dominated by vector boson fusion Higgs to invisible and associated Higgs to invisible. So Higgs Shalom. So you have a vector boson, it's radiated, and then you produce a Higgs. And this guy, right, you know, is again the mono Z final state, right? So if this is a Z boson, you can have a Higgs. This would be decaying visibly. This would decay to leptons. And so this would be exactly the same mono Z that we just did with the spin 1 mediator, except now you have this new diagram, so the cross section is way larger, right? So what are the analyses here? And I won't go into details. Suffice it to say that there is a TT bar plus missing energy search, and tops have lots of decays. A top can decay to a lepton and a B quark and a neutrino, or to quarks and a B quark and a neutrino. And so you can, since you have two tops, you can make categories based on 2 lepton decays, 1 lepton decay, 0 lepton decays. And there's actually separate papers for all of these. And then they quote their sensitivity here, right? So this is the cross-section sensitivity as a function of the mediator mass. And for convenience, we compare it to coupling 1, that's our benchmark. And so people are always, with these analyses, we're trying to get below coupling. So you can see for light mediators masses going up to, say, 300 GeV. I think the 2 lepton and the 1 lepton, the 1 lepton, yeah, and the 2 lepton have gone below 1, and the 0 lepton hasn't. This is for Atlas. It's actually different in CMS. I'll show the result in a second. But again, the strategy is basically the same as all of these other monojet analyses. You have, in this case, TT bar plus missing energy. Your background is actually the same as TT bar plus Z decaying to neutrinos. And in fact, the way we do this is the same scheme of simultaneous fits. So you can have various categories now with Z to muons and TT bar, W and TT bar, just TT bar by itself, and then so on. And you have this scheme of simultaneous fits. And these are all the different categories. I don't know why these aren't showing. But yeah, suffice it to say you have, again, 6 categories trying to constrain a signal region times the final states. So there's 0 lepton, 1 lepton, 2 lepton final states. And in fact, these are split even further. So I think it's about 30, 40 categories. So 30, 40 distributions are all fit simultaneously to kind of predict the backgrounds here and then look for a signal. And then you get these sensitivity plots. And so you can see this is for a scalar mediator. So these are actually comparing all the different final states. So what we're doing here is we're fixing the dark matter to be one specific mass. So this is, instead of doing a 2D mass plot, we just set dark matter to be, in this case, 1 GeV, since 1 is a nice number. And then we can just make our sensitivity plots as a function of a cross-section of a mediator mass. And right, this green is top, this red is monojet. This is, the left is for scalar, the right is for pseudoscalar mediator. And then the orange is the mono Z. So this is basically the equivalent of these triangle plots, right? So in mediator mass and dark matter mass, except now we're just taking a fixed dark matter mass, so just equal to 1. Right, so it's just looking at the cross section at one specific point here. So that's it. Okay. All right, so that's kind of ends the part of the talk I wanted to talk about yesterday. It's basically that, I mean, the takeaway from all of this is that you can take missing energy and any object, and then you can control it because the missing energy usually implies there's a Z to neutrinos decay. And then you can find backgrounds to control Z to neutrinos by either requiring a background where you have a Z to leptons, W to lepton, and photon. And then you can put all of this into some big fit and search for your signal, right? And there's a rich industry now at the LHC of people doing that. But I wanted to ask now, like, given all these final states, given all these models, what's the point of searching for dark matter at the LHC? And perhaps more importantly, what's the point of, like, what are we trying to reach, right? I said, oh, we have this benchmark, coupling equals 1. Is that important? So let's try to ask, how does this play? How do these analyses play in the context of the world of dark matter searches? So I want to go deeper into the models, and I want to discuss some of the issues, right? Why are we using these simplified models, and why are we not using perhaps full models? And then I want to ask more about when are we going to be satisfied? When are these searches actually fully sensitive, right? When can we kind of declare victory? And I also want to talk about other final states, because once you start, assuming models, right, you don't necessarily need to have that model decay to dark matter. You can have a mediator decay to leptons, right? And so we'll talk about that. So I want to start this part of the talk at the Higgs discovery, so 9 years ago. So it was a fun time. I think I'm right there. So, I'm right here. I had VIP seats, right? I didn't have to stay up all night. I didn't Photoshop that. You can't Photoshop that. I mean, I know the person sitting next to me, Valentina, like, I mean, I know her very well. There's no way I would have so, but there are some things that are strange in that plot. So if you actually look in the top left corner here, there are some things that are inconsistent. There are other things I put in here, so you can have fun staring at this. But kind of the bigger message is that since we discovered the Higgs, basically the Higgs has been very consistent with the standard model, right? So this is kind of an old plot. But our star is our standard model, and the best fit is about 1 sigma away. And there's really been not so many hints of new physics for Higgs, but this tells us really a lot actually about dark matter. And I want to explain how this does it, particularly through the Higgs to invisible. And the point of this is actually to go beyond the simplified models, right? So a lot of people don't like these simplified models. There's a lot of good reasons. So I asked this as a question yesterday. And just to put 3 reasons that I could think of on the top of my head is, first of all, they're not full models, right? They're going to break at some scale, right? So you can evolve these up to some scale, but there's going to be a Landau pole. And they're incomplete, right? So that means there are final states typically that you might be missing in your simplified model. And then the other thing that people complain about is that this seems to be an LHC thing. And my reply is just hashtag true, not true. So let's actually look at some full models. But my personal view is the reason we made simplified models, right, to start with was because they're simple. And once you start adding full models, things get very complicated very quickly. And certainly for my taste, they're a little too complicated. So let me take the simplest simple model, simplest full model, right? It's not simplified anymore. And that's just to take a scalar, have it coupled to dark matter, and then have it mixed with the Higgs, right? So this is the singlet mixing model. This is kind of the simplest like extension to the standard model that you can have. And so what's going to happen is that you're going to have your Higgs and your singlet, they're going to mix, and then the Higgs you actually observe, right? The Higgs that we see is not going to be Higgs anymore. It's going to be this H1, which is going to be a mix of a Higgs and a singlet, right? And you're also going to get another scalar, H2, and this is going to be, let's say, it will be dominated by the singlet. We assume kind of there's some mixing that's aligned between the Higgs, but you'll have another scalar. And so you can start to search for the scalar, or you could start to search for the Higgs and look for modified properties of the Higgs. So what happens to the Higgs? Well, once you have this mixing, you can rewrite your Lagrangian, and you're going to get a term like this, right? So now the Higgs that we observe, H1, will actually couple to dark matter, and so you're going to get Higgs to invisible, right? And it's going to couple by this mixing angle sine theta. And then the heavy or the other scalar could be light, could be heavy, will also couple to dark matter. It will decay much more likely to dark matter than the Higgs. We assume sine theta is small. The other thing that happens with this model is that the Higgs now has modified couplings to W bosons, Z bosons, and fermions, right? So we can go back to that coupling plot, right? This guy here, and we can start, just from this plot, we can start to make statements about whether there's a scalar dark matter. So the couplings, and how they deviate with respect to one tell us a lot. And in this case, they'll deviate by, the difference between 1 and cosine theta, right? If cosine theta is not 1. So this gives us some bounds to actually search for it. The other thing is, on top of the simplified models, it gives us other final states, right? So now we can have the Higgs decay to dark matter. You get a branching ratio from this. That's kind of your normal branching ratio with the sine squared theta. And now you can have Higgs on, so you can have your Higgs decay invisibly and radiate a W or Z, and you can have vector boson Higgs to invisible. So you can have both of these. And of course, right, the scalar can do the same things because now they're mixing, right? The scalar, the new singlet and the Higgs, they behave the same. The other thing you also have is you have your simplified models, right? So we have our monojet, right? That still lives here. And we also have TT scalar, right? And just, you can actually take the simplified models, and for these interpretations, you can just recast, right? You can take, in this case, our dark matter coupling goes to some Yukawa dark matter times cosine theta, and our standard model coupling to the quarks just goes to sine theta, right? And so now we can go ahead and let's say look at this model, right, and start playing around. And so you have additional parameters now because we added a scalar, but it's mixing with the Higgs. And so what we can do is we can vary the mass of the scalar and vary the mass of the dark matter. Right? This is the usual plot I keep showing, right? These triangle plots. And we can look at various regions of the phase space. So when this scalar is heavier than the Higgs mass, it will, and the dark matter is heavy, the heavy scalar will decay invisibly, but nothing else, right? When the dark matter is heavy and the scalar is light and the Higgs is fixed, then your probability of decaying to dark matter is basically 0. So this region is almost impossible to probe. This region, you can just probe it when the scalar is heavy and it decays to dark matter. And then once the dark matter is light, and it's, when I mean light, I mean less than half the Higgs mass over 2, then suddenly the Higgs can decay to dark matter, right? And once the Higgs decays to dark matter, you basically have Higgs to invisible. So basically, in the end, you have kind of 3 regions of phase space in the singlet model. You have a region where the scalar decays to dark matter, and you don't have anything else. You have a region where you have Higgs to invisible, and then you have a region that's basically inaccessible. And actually, this region is, there are a lot of papers on this region, and they're very depressing. But so, and then you can start to look at this, and you can start to make bounds. And I won't go through these plots, but suffice it to say, with kind of the same amount of data, with a light dark matter, you can get kind of tens of events at the LHC with a small amount of data, and so you would be able to see a signal. But you would get kind of less than 1 event in the region where the mediator is heavy and the dark matter is heavy, and you would get another 10 times less events when the dark matter is heavy and the mediator is light. So this region is really hard to probe. And then of course you can start comparing, asking the question, well, I just did all these analyses with these simplified models, do things map onto it? And suffice it to say, this legend is super confusing, but these black points here are the simplified model, and these lines here are this singlet mixing model, and suffice it to say they map almost exactly on to each other once you're in the region of phase space where you expect them to. Otherwise, this guy will map onto the Higgs to invisible. Yeah, question?
Yeah, what is the y-axis on that plot telling us?
The y-axis on this plot? Oh,
Yeah.
this is just a normalized cross-section. So
Okay, gotcha.
yeah, so it's just the cross-section of the function pt over cross-section. So it's a differential distribution. Okay. But kind of the I don't want to go into too many details, but the kind of the picture to remember is that for this model, if you look at the bounds, what happens is that because there's mixing with the Higgs, this Higgs to invisible kind of drives the constraints. Right? The Higgs is light, or lightish, and so you can produce it a lot at the LHC. And so this bound tells us a lot about, if we were the singlet mixing model, but more generically, it tells us a lot about a scalar. If there was a new scalar that existed and it coupled to the Higgs. So like a scalar portal dark matter, as people often refer to it. And just by playing with the current bounds we have, you can kind of understand our sensitivity. So a 10% bound on Higgs to invisible which is roughly where we're at now, tells you about the mixing angle. So it has to put a bound on some data at something like 0.7 for 5 GeV dark matter. If dark matter were 50 GeV, you have Yukawa coupling squared here. So this would be 100 times more smaller. Sorry, square root 10 times smaller. So it'd be 0.7. And that's a 10% bound on Higgs to invisible. The Higgs couplings, which I didn't talk about, also put strong constraints, right? We get modifications in the Higgs couplings at the order of 1 minus cosine theta. And then 10% bound, you can play with the math, would give you a sensitivity to sine theta of 0.3 for any dark matter mass, because the coupling gets modified, and this doesn't actually impact, right? The dark matter mass is not there, right? It just gets modified by cosine theta. The dark matter doesn't play a role. So you can get constraints from just the Higgs couplings themselves. And that's kind of important role, is that when we're trying to look for a full model, all of the final states play a role, right? Not just invisible, all of the final states. And we're going to see this come back over and over again.
Another basic question, what does a 10% bound actually mean?
So this means, 10% bound means that I'll come back to that in a second. So a 10% bound means that when you make your limit plot, it means that your observed value for your limit is at 10%, which means that you have a 2 sigma exclusion probability. So there's a 95% chance that there's no signal at that value. So
Got it. Okay, thanks.
I mean, some people will play around with the numbers of sigmas. There'll be a 1 sigma exclusion, 3 sigma. Depends on how conservative or aggressive you want to be.
Sorry. So this 10% bound is not 10% CL.
No. This is 10% on the, sorry. This is a 95% CL
Yeah.
on the branching ratio of Higgs going to invisible at 10%. It's not, they're completely two different things. So this is, so look at this plot. So this is the branching ratio of Higgs to invisible. The y-axis here is branching ratio, but the bound is the confidence level of this bound. In this case, we choose 95%. So this plot says that at the point here is observed. So this plot says that at 26% branching ratio of Higgs to invisible, there's a 95% confidence that there's no signal there.
Right, so the 10 is the value of the vertical axis.
Yeah, so the 10 it would be, so yes,
Yeah, okay.
so this is an old plot. And so we're now at 10.
Right, okay.
Or, I'm sorry, we're not publicly at 10.
Oh, right, okay, cool.
So actually, no. All right, Atlas is at 11. So it's okay. Right? Atlas is at 11. Atlas is public. They're ahead of CMS in this one. But I can tell you in like a few months, we'll be at 10.
Right, so this 10 is the proper observed upper limit. Okay.
That's right. That's
Okay,
right.
okay.
See observed upper limit. So another way, maybe an easier way to think about it is this x-axis here is your branching ratio of Higgs to invisible. And then this y-axis is just your significance, right? And so you can now scan this is the likelihood scanning various final states, right? And then the black is the combined. And so in this case, what you see is when you scan the likelihood, there's actually a best fit that's non-zero, right? So there's a minimum at like 10%. And then you see that quickly as you get to larger branching ratios, you have an exclusion. So So, and basically we just draw the line here, right, at 2 sigma, right, which is 3.96, right?
Okay, thank you.
Okay. So, suffice it to say, the Higgs to invisible analysis. So I won't even really explain it because there's really not so much of a point. But the Higgs to invisible analysis is exactly the same as the monojet. We do the same scheme of getting 1 million control regions, and then trying to constrain Z to neutrinos. Z to neutrinos is the dominant background, and there's some tricks, as there are with every one of these analyses. So for example, you now have diagrams like this, where you have vector boson fusion producing a Z. And so you have to add additional uncertainties to account for this, right? And just as a point, right, W vector boson fusion, which is a solid blue, is different than Z vector boson fusion, which is this cyan color. And so these all constrain the sigma region at different rates. So this is actually your sigma region, and you have, it's supposed to be the same color scheme as the monojet, but you see there's more colors because we have these additional additional production nodes. Okay. So, and then, these days, people just care about the combined result. So this is the Atlas combined result there at 0.11, and that's combining a few of these final states, not all of them. The CMS one, so these are actually, I think, all the Higgs invisible final states. So it's this vector boson fusion, Higgs to invisible, Higgs strong, Higgs to invisible, so the Higgs decays invisibly, the Z decays, or the W decays to quarks or leptons. And then you have Higgs to invisible monojet, where Higgs goes to invisible, and you just radiate a jet. And all of these have set different sensitivities, and you can look at which ones are more important. So just for example, the monojet is actually the least sensitive analysis here, right? So the branching ratio now, this result is public. The new one is at like 0.3 Higgs to invisible, but the new mono Z, right, where the Z goes to leptons, is at a exclusion of something like 0.18. So these values have been like each final state plays a different role. Okay. So what about more complex models? So there was an effort. There was an effort to add a scalar complete model, and so that gave us Higgs to invisible. There's also been an effort to add a pseudoscalar complete model, and the way you embed this guy into a complete model, the simplest way that people know of is a 2 Higgs doublet model, and despite the nice short name, the actual model is very complicated. So you end up with 5 different new Higgs scalars or pseudoscalars, right? So you end up with these 5 different Higgs-like bosons, and five new particles means you have a lot of parameters, and things get really complex. And this is actually the point of the simplified models, was we wanted to kind of avoid, spending 1 million years like probing parameters, and just looking for excesses in the data. Because in the end, the signal is just a hypothesis you interpret your data with. So in the case of a 2 Higgs doublet model, you still get final states like in the simplified model, right? So this would be allowed in the simplified model, right? Mono Z. And this guy would be allowed in the simplified model. This is a mono top. But you also get new diagrams like this thing where you have a top and a jet, but you have a charged Higgs boson exchange, charged heavy new Higgs boson. And you also get things like this where you have resonant mono Z, where you have a Higgs decay to a pseudoscalar and a Z. And then this thing is resonant at one of the new scalar masses. So you end up with more diagrams. But it turns out that the conclusions are quite similar to just the simplified model. Yeah, question?
So I guess I'm not exactly sure what you mean by a simple model versus a complete model. What makes this complete?
Yeah, so the big thing about this is if I were to just take a model where I have a pseudoscalar and I just add core couplings to this pseudoscalar, and I evolve this up to some scale, the model breaks down, right? There's going to be like a Landau pole. right? There's going to be a divergence of some sort, right? And so the way you want to, if you want to be able to evolve this up to like a high scale, you need to embed this into a complete renormalizable model, right? Like the 2HDM, right? So, and there's like, 50 years of literature of new physics models that you can put these things into.
So I guess when I look at that L-chi on top, if I'm looking for something that's non-renormalizable, I'm looking for some kind of dimension 5 operator, but that's just dimension 4, right? So how are you saying that this is?
No, so if you, sorry, it's not just this term, right? This is just Aug10. If you add like couplings to the quarks, right? Right, so the couplings to the quarks are dimension 5, yeah. So,
Okay. Okay, fine.
yeah.
He wants gauging on it.
Yeah, to have gauge invariance, right?
Sure.
All right, so I mean, question.
Yeah, sorry.
This 2x standard model, isn't that already excluded? I thought that when measuring the rho parameter, it should be 1, but this gives you 1/2, and therefore.
No, the 2x model is not excluded. There's like, I mean, there are 2x doublet models that are excluded. This one is actually 2x doublet model plus the pseudoscalar that decays to dark matter, right? I mean, there are, I'm not sure which model you refer to, but for sure this one is not excluded. I mean, there are a lot of regions of phase space where it is excluded, but it's not completely excluded. I mean, there's too many parameters here. All right, so I mean, I was kind of hesitant to talk too much about this because we can have discussions all day about this thing. And it's honestly like me as an experimentalist, I kind of, it becomes, I get less excited. But my conclusion with all of this is that what I care about is I really don't care too much about the model. I care about making sure that we have all the possible final states so that when we look at the data, we can interpret the data correctly. So I want to make sure that we have, if we have a resonant mono Z final state, we should look for that, right? If our mono Z final state is non-resonant, we should just look for those, right? So the key here is to make sure you have all the topologies. How you interpret this is, something you can spend a lot of time on. But when you don't have if there's no excess, right, you can interpret it a lot and make bounds, but there's, it's just an interpretation of a lack of signal. And in the case of 2x doublet models, right, for at least this one, right, the dominant channels turn out to be this mono Higgs, mono Z final state, yeah?
So we could construct a dark matter model to give us basically any possible final state, right?
That's right.
So I guess I'm wondering, with your point about like experimentalists care about all possible like constraint or identifying all possible final states, isn't anything a possible final state?
So there's some final states that are better than others.
Why is that?
Because I said so.
Okay. Thanks.
I mean, it's like Animal Farm, right? Right? All animals are created equal, but some animals are better than others. So I mean, that's the point, is that at some point this goes from like a talk on, ideally we want to search for everything, right? All the time. But there are some final states that you might think are better than others. And it's kind of a choice, kind of intuition. There's no, I don't know, that's all I would say. I mean, I personally care about looking for as many final states as I can. So in the case of this 2HDM, right, which is a very well-motivated model, and people often say this is the simplest way to embed a pseudoscalar into the standard model. You can get, it turns out your bounds for mono Higgs and mono Z are the most sensitive functions, right? And you can make a plot like this, where I'm varying one of the scalar masses and fixing the other 3 to be constant. And then I'm varying the pseudoscalar mass. And you can see you can get bounds as a function of, so for a light pseudoscalar mass and a heavy pseudoscalar mass, right? This, you can get exclusion bounds here, right? For some fixed set of couplings. There's so many things that are being fixed here, it gets confusing. Because you also have additional, you have this mixing angle sin theta, you have tan beta, right? The ratio of the Higgs does. So in any case, you do get these new final states. Yeah.
That is what we was, I think, the next thing we're gonna say. Yeah, how do you keep track of the thermal production of that matter, like in those sophisticated?
All these production models?
Yeah.
Yeah, so the best way these days is you write out your Lagrangian and then you generate all the diagrams and then you look at all the functions. I mean, it's systematic, right? Right, these days we have, like, if you have a specific final state, we have things like MAGRAPH, which will write out all the leading order combinations. And
Yeah, but I mean, I'm referring to the thermal production of that matter for modeling and stuff.
oh, how do you do that?
Yeah.
Next.
Yeah.
All right. So the next thing is, now you've made your favorite complicated model, right? And now you thermalize it and understand it. And I guess you guys have gone through how to thermalize it. The kind of 2-slide derivation that I'll show is that you can go from the Hubble constant, right? Sorry, you can get a distance by just noting that the number density times the cross section. 1 over that is a distance, right? When you're thermalizing. And you can relate this distance to the velocity of the particles when the universe is expanding by multiplying it by h, right? And so then what you can do is you can get that h is going to be proportional to the velocity times the number density of your matter. So this could be dark matter times the cross section. And then I'm sure you guys know that rho is proportional to temperature to the 4th. I'm going through this quickly. So, and if you want to do number density, you get rid of the temperature, right? And so then just from the Freeman equations, h squared is going to be proportional to rho. And so that means that h squared is going to be proportional to temperature to the 4th, right? Times some constants. And h, we said, was proportional to the number density times the cross section times the velocity, which means that the number density for dark matter at freeze out is proportional to the temperature squared over the thermalized cross section times some constant. So I figure you guys know this, but the important thing out of all of this is that the dark matter density is just going to be equal to some constant over sigma v, right? So to first order, right? So this is why, right, on these indirect detection plots, right, where you show this on the y-axis, right, your thermal relic is roughly a constant, right? It's not completely, there's some change, right, that comes when you actually do this correctly, right? But the nice thing is that we can think of the dark matter, and we know the dark matter density. It's just going to be a constant divided by this sigma v. And this allows us to actually start kind of making estimates from a model. So now we have a model, right? So let's say we have a simplified model and we want to thermalize it. And the way we do this is we just have dark matter annihilate, produce your mediator and Decatur quarks. And you have a bunch of parameters here, and you can just write down the cross section from this, right? It's just coming from this diagram, and you get this guy, right? Which is just the usual Breit-Wigner and some couplings. And so this is how we can get our rate of dark matter, because we know that this guy is going to be a constant, right? So we know what this guy needs to be to get the right. If this dark matter, we know what this dark matter density is. So it's going to be of this order, right? Sigma v. So this guy is a constant. And so you can actually start playing games and solving for the mediator mass and the couplings in a relation. So let's take the case where the dark matter mass is not equal to half the mediator mass. So this term is non-zero. And let's just write this in an even simpler form, which is just this. So if this guy is, let's say, small, and this guy is large, this whole term becomes 1 over mass to the 4th. And this guy becomes this stays the same, right? GDM squared, GQ squared, and this is a constant. Well, we can just take a square root of all of these, and we just get that GQ times GDM squared over the mediator mass squared is a constant. And this relation basically drives the history of dark matter searches at the LHC over the past 10 years. The point being is that we started caring about M and fixing the couplings to something large, right? We almost always fix this dark matter coupling to 1 because it's a nice large number. And then we started with a large GQ, right? A lecture week size GQ, something on the order of 0.25. So what does that mean? Well, if this needs to be a constant, that means a large GQ also means that you have to have a large mass, right? So this is GQ squared over mass squared, so they're linear. So what this also means is that if I start making the coupling smaller, I have to make the mediator mass smaller. And so as we take more data, right, at the LHC, we keep finding that, and there's no signal, we keep finding that, well, we're sensitive to smaller GQs and we're sensitive to smaller mediator masses. And a lot of people these days have said, well, let's take the limit where this becomes really small, right, GQ. Well, then our mediator mass becomes really small. And this has led to the light dark matter revolution, right? The past 10 years, people have decided that every single device in the world has dark matter in it, or at least interacts with dark matter, including like the clock on your phone. And so they've been searching for dark matter. And so, I mean, you guys, I'll talk about the accelerator version, but I'm sure you've heard about like these atomic clock searches, just to take a random one. Or there's one where they want to measure the dark matter wind in like a mine, right? There's the gravitational dark matter. But it all basically boils down to this relation, that your coupling over your mediator mass has to be small coupling means small dark matter. Now we can go back to these cross sections, right? And we can start to actually translate, or we can look at this in the context of our simplified models, right? These are the forms for all of these. Yeah, you can look at these offline. Just as a note, right, the scalar is velocity suppressed for this diagram, so you get something slightly different. And you know, these others have kind of similar forms. You can also look at this when you're thermalizing. You also have to care about a few other diagrams. And the one that's important is really this double mediator production. And the important thing here is that so the previous one has interesting features when the mediator is double the mass of the dark matter, right? You get this resonance. When you have double mediator production, right? The important feature is when the dark matter is the same mass as the mediator, you get a resonance. And again, right, in this case, the pseudoscalar and the scalar are velocity suppressed, vector and axial are not. So now what we can do is we can start actually making plots, right? And we can take the same plots that I've been making, you know, in this whole talk, dark matter mass versus mediator mass. And then we can scan these, fix the couplings, and compute the Rayleigh density. So this z-axis on this plot is the Rayleigh density. And the way we do this, the fast way, is with an extension of MadGraph. I like to use this MadDM. Some people like to use this micromegas program, which does the same thing. So MadDM, you know, I just want to shout out to my friend Mihailo, who's not in physics anymore, but he set up MadDM, and it's been very useful for me. And so you can then start scanning, making plots like this. So you have a mediator mass, dark matter mass. Your z-axis is the Rayleigh density. The Rayleigh density that we care about is 0.12. So it's this thing, like blue color. Can't really see too much in this, but suffice it to say that the regions where with these simplified models, you can't go because you get an overabundance of dark matter. This is typically the region where you have light dark matter, right? And can have a heavy mediator, so below this diagonal. The diagonal here is where the mediator mass equals 2 times the dark matter mass, and you get this resonance. And so dark matter can freeze out at a later time scale. And and then this region, the dark matter, let's say freezes out early, the cross section is large, right, for dark matter annihilation to mediator. And then you have this region here, which is dominated by this double mediator production. So, and then you can make diagrams like this, right? So the left here is for a pseudoscalar or scalar mediator. Actually, this is a scalar mediator. And you have various features. Kind of the important features to remember are the features where you have resonant annihilation. This is when the mediator mass is equal to double the dark matter mass. And you have the other line where the mediator mass equals the dark matter mass. So we have the double mediator production. And that's true this is for a pseudoscalar, this is for an axial vector mediator. Again, you have these same two lines. So along the line of mediator mass equals 2 dark matter mass, you have resonance. So you have this kind of chimney where you don't overproduce dark matter. Outside of this chimney, you do, right? So this region you overproduce dark matter. This region you overproduce dark matter. And then again, along this line, you overproduce. You don't overproduce dark matter. Yeah.
What are the equations that are being plotted on the left?
Oh yeah, these guys.
Yeah.
They are these equations. The equations I just showed you. So this guy. So this is equation. So this one is equation 4.3, and then this guy, that's equation 4.2.
So should we be looking at this plot as like an exclusion plot?
So it's not so this is, I mean, we always make our exclusion plots on these axes, but this is really the you can call it the relic exclusion. So basically above this line, like in this little triangle below this line, we have an overabundance of dark matter. So the cross section for these production becomes sufficiently small. Yeah, sufficiently small that the freeze out is at an early temperature. And so you get an overabundance of dark matter.
Okay, thank you.
Hello. So I do not understand why we use here the thermal relict entity. I mean, for colliders, we try to produce them, but there's no restriction to any kind of thermal relict entities or not.
Yeah, so these are just as a guide to compare your models. You can basically, it's very easy to tweak your model and destroy these plots, right? But we wanted to come up with some benchmarks to compare the collider searches, right? Let's say I exclude coupling 1. What's the importance of coupling 1? Well, the importance of coupling 1 is that for this simplified model, right, you can't produce dark matter that's light, right, in this instance. It's just a guide. It is easy to remove these plots, but it's very satisfying to say that you've excluded, a simple model at some relic line, right? I mean, it's not. It's like in some ways people use this as like a benchmark, but it's very easy to avoid these, right? I mean, I could, I could, for example, make my dark matter unstable and decay to another dark matter, right? And I can play with the couplings, and then you can change these relic bounds. Well, it turns out it's a little tricky, but you can change these relic bounds, right? How you want. There's a lot of freedom. If you're a model builder, right? There's a lot of freedom to make this plot look different. But if you're trying to just kind of cast your results in something simple that's easy to digest, it's a nice way to look at this. And it's a nice way to kind of drive your analysis. And I just want to actually, yeah, so let me go a little bit further into this. I'll skip this slide. Suffice it to say that, actually, let me know. So this is actually when we run med-dm, I get a plot like this. So again, this is a nicer version of the plot I was just showing, where you have the relic density as a function of mediator mass and dark matter mass. And then what you can do is you can start varying other things. So you can vary the coupling to standard model, and you can see that your bounds get stronger, right? So you actually, this line here is within this line is the region where you wouldn't overclose the universe. And you can see that this bound is actually shrunk. So these axes are the same. And this is the left is for vector mediator, the right is for an axial vector mediator. You can see that it shrinks. And this, you can also look at this in the context of scalar and pseudoscalar mediators. And just to kind of put a point to the scalar mediators. So a friend of mine, he made a plot similar to this about 5 years ago. And he basically said, look, when dark matter is light, the scalar, you can't actually get the right thermal relic for scalar mediators. And he's made the strong statement saying that we shouldn't even look for scalar mediators, right, when the dark matter is light. And some people actually take this very seriously. So I've been in meetings where somebody said, oh, let's not care about the scalar mediators because it's very hard to get the right thermal relic with these guys. But of course, right, if the dark matter is heavy, and the scalar mediator is light, you have basically a free zone where you can do whatever you want, right? And you're not going to overclose the universe. Yeah?
Thanks. Where does that exclusion come from at the top?
This guy?
Yeah.
So again, it's the same two lines that I showed you before. So one is at dark matter mediator mass, M mediator is double dark matter mass. And this line here is M mediator equal dark matter mass. So this is double mediator production. So.
Sorry, I still don't quite get why that little top region is excluded though.
So what happens here is that in that region, double mediator production starts to dominate, double mediator production turns on here and it's allowed here, but here the cross-section for double mediator production is turning on. And so in fact, and the cross-section for single mediator production is turning off. And so you have an exclusion here. So the cross-section gets large.
Okay, gotcha, thank you.
So yeah, the cross-section gets small, sorry, large, large. Okay, now the other point, right, to kind of go to your point about why are we making these plots with a simplified model, is that if you embed these into full models, right, the relic bounds tend to not change too much, right? So here's this singlet mixing model, right, that gave us fixed to invisible. And the difference between that and the regular model is this blue and this gray. The gray is the simplified model, the blue is the mixing. And in fact, the bounds become a little bit stronger, but suffice it to say they're similar. And you can draw, there are more resonance lines, so you can look at these lines, you can look at your model and you can play games with this. You can at least look at where all the features are. And I'm not even going to talk about Tube's double model. Suffice it to say is that the pseudoscalar plot I showed you, this one, this guy, it basically is the same for the full like 2HDM. So you can stare at these 2HDM plots where they're varying many things, and you'll get to the same conclusions. I think that's all I want to say. Yeah, it's basically this. The other thing to mention about these is that in these kind of simple models, there's also an upper bound. So if you actually take, let's say I wanted to kind of allow a heavy mediator and I take really large couplings, right? So larger couplings means heavy mediators. Well, it turns out that there's still a maximum mediator mass that you can have. And then beyond this maximum, the universe is always overclosed. So the nice thing is that you actually have upper bounds. And so if you're trying to build a new collider, like a 100 TeV machine, and you can basically get up to this region, well, you can basically exclude all simple models of dark matter definitively. So there's an upper bound. So, all right, I want to go a little bit further into this about the relic density. And, going back to our formula here, if we set this to a constant and we expand this width term in terms of its couplings, and you want to know, and then what I'm going to do is I'm going to fix the mediator mass and the dark matter mass. So I'm gonna fix these. These are all gonna be constants. And then what I'm gonna wanna do is I wanna solve for these couplings, GDM squared and GQ squared. This is a constant, and I wanna solve for these values. So if I solve for this, you end up with a quadratic equation, right? There, you have this width term, which is just a function of the dark matter mass squared and the GQ squared, right? This is the width of everything. And then you have these guys here, which are a function of GDM squared, GQ squared. And so you can, if all of the rest of these things are constant, you end up with a quadratic, and you'll have two solutions. You'll have a minimum coupling and a maximum coupling. And if this guy is set to the Rayleigh density, you'll have a minimum possible coupling for the Rayleigh density and a maximum possible Rayleigh density for the coupling. And just to kind of conceptualize this, here's this same variation. So what I'm doing here is I'm fixing the mediator mass, I'm fixing the dark matter mass, and then I'm plotting here the Rayleigh density as a function of one of these couplings, GQ. This is the 2D version, right? So GQ, GDM. And what you see is you get a quadratic, right? And you have a minimum, and you have two solutions for this specific Rayleigh density. So what I can then do is I can vary the mediator mass and the dark matter mass. So I'm going to vary it to something light, like 10 GeV. And so now what happens is that you have a maximum allowed coupling to get the right Rayleigh density and a minimum allowed coupling to get the right Rayleigh density. And that's true if you vary the dark matter coupling, GDM, or if you vary the standard one. So the nice thing is, if we're trying to search for dark matter, and we want to come up with like a benchmark for what's the smallest coupling we need to get to kind of exclude the most simple models, we can take this minimum, right? And this minimum can be a driver for our sensitivity. So this kind of minimum, this dark matter or matter to dark matter mediator coupling, this minimum kind of drives all of the searches that we do at the LHC, but also all of the light dark matter searches. And this minimum is going to show up in basically every plot that I show for the rest of these lectures. And you can solve for this. In fact, if you want a fun exercise today, just pick a model and solve for the minimum, right? You can solve for this analytically, right? Just from this formula. So that would be a fun thing to do. And so you get the minimum. And in fact, you can vary these mediator masses, and you can get to smaller and smaller bounds. And there are instances eventually when you get to a small enough mediator mass, like let's say a dark matter mass that's close to the half the mediator mass on shell, it becomes possible that this coupling can go to really small values, right? And that's kind of the scary region where it's basically impossible to exclude this model. And so then you can make a 2D plot that looks like this. And so this 2D plot has all the features I just showed you. There's a region here where the double mediator correction turns on, where you have no minimum. And then there's various regions here. So there's a region where the dark matter is light, where the minimum coupling is huge, right? There's regions here where you're on the resonance of this diagram. And so the allowed coupling becomes very small. And then there's regions up here, right, where the allowed coupling is quite large. And again, you can have a minimum coupling to exclude dark matter. And depending on the model and the final state that you're looking at, people like to draw lines from these plots. Here's the scalar version, so it looks a little different. So you actually have a region here off shell where you have, let's say, large couplings, or you have a large minimum coupling, right? And just the scale is different. So you have couplings greater than 1 here. And the nice thing is that this kind of tells us where we should look for dark matter under these simplified models, right? So this tells us this region here where dark matter is light. You have a lot of flexibility. These regions here where mediator masses and dark matter is heavy, the couplings have to be very large, and we very likely would have seen something at the LHC. And so this kind of tells you where to explore. And these kind of features down here have been pushing or getting people very excited for light dark matter. Right? This is one of the main motivations. And you can do this for these simplified dark matter mediators. You can make a plot like this for each of them. And you can look at the various features. Suffice it to say, axial vector by itself is very hard to make. You need very large couplings to get the right dark matter, or to not overclose the universe. Or the minimum, sorry, whatever, the minimum coupling needs to be large. The minimum coupling for vector mediator needs to be smaller. And the kind of benchmark is 10 to the -2 in these units. Scalar and pseudoscalar, the benchmarks for minimum couplings are sort of 10 to the -2, 10 to the -1. So if you can get down to those couplings, you're excluding kind of most generic models. And this allows us to kind of drive our searches and use these as benchmarks to see how sensitive we are. Okay. And just as a note, because this is going to show up a lot, is that a lot of people like to just take a single line in this 2D plot, right? They just take this dark matter mass equal to the mediator mass over 3, and they like to plot this line onto their dark matter exclusion plots. And they make plots like this. This is the LHC version. And the LHC version, you have this blue line here is your minimum coupling. So below this, the universe will always overclose. And so the strategy, and then these here are exclusions as a function of mediator mass. And so the strategy is to get this exclusion to cross this line. And for vector mediator, we're very close. For axial vector mediator, we've actually crossed this line. And we basically excluded along this diagonal all dark matter, let's say the kind of conventional dark matter model that would give you an axial vector mediator. And we've excluded this by a bit. So the strategy for the vector mediator is to push these bounds down to cross this line. And I don't know if I'll make it through in this talk, but you'll see that we've actually already crossed this line. Right. And in fact, yeah, I just overlaid the current results. So this is the current monojet result that came out a few weeks ago. And you see it's starting to get to this line for the vector mediator. But you'll see there are other ways to exclude it. Yeah, so this kind of brings me to the last thing I wanted to talk about today. I don't know if I really have time to do it justice. Yeah, let me start though, which is how do we actually go after the instances? So, I talked a lot about the monojet search and all these MET plus X searches. And these are the cases where dark matter is light and the mediator can decay to dark matter. Right, these MET plus X searches give us this triangle, right? Where we can exclude a mediator and we can exclude dark matter when it's lighter than the mediator. So what about this region up here when the dark matter is heavy? Well, when the dark matter is heavy, your mediator doesn't decay to dark matter anymore, but your mediator still decays. And so you can actually use other final states. So here's your original diagram that we used to search for monojet. And we have a coupling from of quarks to the Z prime here. So what we can then do is we can just take this coupling and we can move it or clone it over there. And now you have a Z prime decaying to quarks. And in fact, this is just a dijet, right? And you don't even need an ISR jet anymore. You can just look for this diagram, right? So Z prime decaying to 2 jets. And this gives us a nice resonance, right? The mass of these 2 quarks is going to be the mass of the Z prime. And depending on your couplings, right, for kind of the conventional couplings we use with the LHC, the branching ratio of Z prime to quarks is about half the branching ratio of Z prime invisible. So you actually have a lot of these dijet events, right? So how do we do this? All right, here are the branching ratios. Skip this. So how do we do this? Well, we look for a Z prime decaying to quarks. These quarks will then shower and will give us jets. We just look for 2 jets. And then what we do is we take typically the 2 highest energy jets in the event. we take the mass of that and we look for a bump, right? That's it. There's some details here about how we do it. The jets need to be central, but we just look for a bump. One thing to note though, is that at the LHC, we take a lot of data. So we actually collide at 40 megahertz, but we actually take data at 500 hertz, we save it to disk. And so all of this data reduction, we kind of remove physics. And this, we call the trigger. And basically to get down to this 5 hertz, we do various granular selections of events. So we do a very quick scan of the event and do like a coarse look at it and try to determine if it's interesting or not. If we think it's interesting, we then do a more finer scan. And only if that event is really interesting do we save it and get to look at it in detail. And effectively, the way we think about this is that to look at the data with your trigger system, you get to look at all of the data, right? So the full range of data coarsely. And the thing you'll see at the LHC is that typically most collisions are low energy, just protons grazing off each other. And so they occur at a very high rate. As you go to higher energies, the rate becomes lower. And so typically the highest energy events we get to keep, the intermediate events, we only get to look at with our kind of intermediate reconstruction. And all the events we only get to look at with a very coarse grain reconstruction. And so that's certainly the case for these events because there are a lot of backgrounds. And so we can only look for really high energy jets. And so to select these events, we require a trigger. We require a trigger for these events to be high energy. And in fact, the minimum energy we can get for these jets is about 500 GeV, which means that we can only really look for a Z prime that is selected completely above a TeV. And so we did that. I'll get to that in a second. So we do that, and so we take the dijet mass, and then we have this Pauling distribution here. And so we just fit this to a function. We fit this to this function. We call this the dijet function because it fits dijet. It also basically fits anything that's sloping on like a falling background. And then we look for a signal. Our signal is just a resonance on top. And if you want to form for it, this is a Breit-Wigner convolved with a Gaussian or a Voidian. So that's like a nice shape. But typically we simulate signals, right? And so we just look for a bump on top of this. And then it's kind of hard you can't see a bump in this plot because the range is so large. But you can look at the ratio plot here and you can try to look for a bump. And you don't see anything. You see like, oh, there's a big deficit here, but it's just one bin and your signal should be a few bins. So this is perhaps the largest excess here. There's like 3 bins that are like one signal up. But it's not something to get too excited about. And so that's how we search for it. This is the dijet. This allows us to probe the highest mediator masses. But if we want to go further, right, we have to start playing games. So the first thing we can do is we can actually try to do this analysis while we're actually taking data. So this is during what we call a trigger level analysis. So while we're processing the data, we look at these coarsely reconstructed jets, and we try to just make a mass with these coarsely reconstructed jets. In our system, we don't get to save the full information of these events to disk. So we just have to look at we do run the full reconstruction with coarse granularity. And we can save the reconstructed objects. So what we do is we save the coarsely reconstructed jets, and then we just take a mass offline. And so our normal jets that we get to actually save are these red lines. And then the ones that we save, like the trigger objects that we save, are these points here. So we're able to push our mass range down from like a TeV to something like 500 GeV by looking at these objects while we reconstruct them in the trigger. Yeah.
Thanks. So if the LHC saw something interesting in these coarse dijet searches, how big of an undertaking would it be to somehow change the trigger so that you could look at lower energy digits?
Yeah, that's a great question. So, yeah, let's, actually, you can see it in this plot. So, this is basically a rate, it's about a kilohertz, right? To get to events that are in this red line. So the integral of that is a kilohertz. If you take the integral of these points and divide it by the integral of this, that would be the increase in events you would have. And it's on the order of a factor of 10 more. A factor of 10 more means a factor of 10 more computers. The current computing cluster that makes these core screens costs about $10 million. So the cost would be about $90 million. So
Got it, okay, thanks.
I just did that calculation. So yeah.
But I'm assuming.
Oh, sorry, I turned it off.
I'm assuming this is only software triggers, so you're throwing away a lot beforehand, right? With the hardware triggers, I assume that
Yeah.
change the picture, I guess, or does it?
No, the software to go down here with the software triggers, you need more computers. You're limited by computers, right? So there's a hardware limit. The hardware limit is at the end of this plot, right?
Okay, you're only throwing away stuff like below this mass region with the hardware trigger, so you don't deviate this picture in this region.
That's right.
Okay.
Yeah, so the hardware trigger starts here. So all of this could be done at the software trigger level. The hardware trigger, you can actually push it further. But again, the software trigger would have to be large enough to handle that. And the hardware trigger would also be larger to handle that too. Suffice it to say that, I could talk about this all. This is what I do most of the time. This is where most of my funding comes from, is how do we make the trigger better? I'm happy to talk about ways to actually do this. Like the new thing that we're thinking about doing is basically going from this core screen to the full reconstruction at the kind of software trigger level. But we're at the cusp of being able to do this right now. So we need, basically, it looks like we might be able to do it if we have GPUs in the software trigger. But so I just made a very strong statement that I'm not sure I'm ready to defend. Yeah. But suffice it to say, by just doing these software trigger, like these trigger level analysis, we can push this down to 500 GeV. If you want to go even lower, it's already getting late. If you want to get even lower, you can do a third jet, and you can look for that. And this brings you down here. And if you want to go even lower, you can do a photon, right? And then now that brings you all the way down to 200 GeV. And so that's where I will stop. So, questions? Questions for Chris?
When the LHC was designed, I think 10 years ago, the computer, from the 10 years now, the processing level changed much, the trigger power that you have.
Yeah.
The new processors impacted this or no?
Yeah, so if we were to take the current the computing from 10 years ago, and run it with, so between then, the computers upgraded and the IHC upgraded, right? And so the beam intensity is it's like 2 orders of magnitude higher than it was back then. If we were to take the current computing from 10 years ago and make this plot, instead of 1 TeV, this would be at 2 TeV. It's that big of a difference. And so this is the next generation of computers we're talking about. The hope is we can go from 1 TeV to 500 or 700 GeV, that kind of level. And we're going to increase the beam intensity by another order of magnitude. So both of these basically keep fighting each other. But there's some fun problems here because Moore's law is not helping us anymore. So there's a big fight. In fact, if you guys are familiar with Dennard scaling, that's really the thing that's we're struggling with. So,
Anything else? No, let's think, fill again. Very comfortable.